Hi, Mark Donovan here from Falcon Imagery, and today I'm going to go over the topic of pressure altitude and density altitude. Both these types of altitudes can be confusing to understand what they are, why we care, and how to determine them. And I'm going to answer all of these questions in this video. So follow along. All right, pressure altitude and density altitude explained and how we determine pressure altitude and density altitude. First of all, we need to understand that there's an international standard atmosphere that's used for manufacturers and pilots to understand how the aircraft is going to perform. So the standard atmosphere is 15 degrees Celsius and 29.92 inches at sea level. Regarding the temperature, it's 15 degrees Celsius or 59 degrees Fahrenheit. I'm going to talk today in degrees Celsius, which that is typically what's reflected in today's modern aircraft performance charts. This particular definition of an international standard atmosphere, or ISA, is known as the standard data plane. So at sea level, with a standard data plane, you've got 15 degrees Celsius and you have 29.92 inches of mercury. This is what is used for determining the performance of any aircraft, be it a manned aircraft or even an unmanned aircraft like a drone. It's also important to remember that barometric pressure is normally reported in inches of mercury, but it's also reported in millibars for, let's say, surface analysis charts, hurricane type, low pressure, high pressure analysis charts, etc. So we really need to be aware of pressure being reflected in millibars as well. Let's talk about altitude types and the perfect versus real world atmospheres. So first we have indicated altitude, and this is read directly off the altimeter in the aircraft. Then we have pressure altitude. This is the altitude of the aircraft above the standard datum plane. And then we have density altitude, which is pressure altitude corrected for non-standard temperature. And then we have true altitude, which is the vertical distance of our airplane above sea level. And then we have absolute altitude. This is constantly changing. And this is the distance of your aircraft above the ground, expressed in feet AGL, or above ground level. In the perfect world atmosphere, we have at sea level a temperature of 15 degrees Celsius and a barometric pressure of 29.92 inches of mercury. With the temperature dropping 2 degrees Celsius every 1,000 feet we go up in altitude, and the mercury, or the barometric pressure, dropping 1 inch of mercury every 1,000 feet in altitude. That is known as the standard lapse rate. As you see in this picture here, we have a column of air going up into basically space, or in this case up to about the tropopause. And I should say the tropopause is really the area where you no longer really get that standard lapse rate of 2 degrees Celsius drop per 1,000 feet or an inch of mercury drop per 1,000 feet. So the troposphere is basically from the surface up to the tropopause, and then from the tropopause up, you get the stratosphere. The tropopause line, or marking those two types of atmospheres, ranges anywhere from 20,000 to 60,000 feet, depending if they're at the north or south poles versus the equator. In this perfect world, the density altitude would equal the pressure altitude, would also equal the indicated altitude. However, we don't live in the real world most of the time. In the real world, pressure and temperature are constantly changing due to high and low pressures and warm and cold fronts, as depicted on this chart on the right. You can see there a small depiction of a low pressure and a high pressure. Just as a side note, low pressures rotate counterclockwise up and inward, and high pressures rotate clockwise downward and out. But for the changes in pressures and warm and cold fronts, we don't necessarily have a standard data plane condition going on. The lapse rate is still typically about 2 degrees Celsius per 1,000 feet in elevation, and we lose roughly an inch of mercury as we go up every 1,000 feet. But we're not starting at that baseline at 15 degrees Celsius and 29.92 inches of mercury. It is whatever the atmosphere is that day when we're out at the airport. So what is pressure altitude? Pressure altitude, again, is the altitude of the aircraft above the standard datum plane. Why do we care about pressure altitude and density altitude? Because aircraft manufacturers and pilots need to have some standardized value to base the performance of their aircraft and their aircraft engines to see how they're going to perform in climb and cruise and fuel burn and time and route and so on and so forth. So they've basically tried to come up with a standard reference for all aircraft manufacturers to compare the performance of their aircraft, and for pilots to use that information to judge the performance of their aircraft when they're flying. Now the formula for pressure altitude is the indicated altitude plus the difference in 29.92 inches, the standard data plane pressure, minus the difference of the altimeter setting or the barometric pressure reading that we see at the particular field elevation that we're at. And taking that delta difference between those two numbers and multiplying it by 1,000 and either adding or subtracting it to the IA. When would you add this difference to the IA? Well, when the pressure's lower, we would add it. And when the pressure is higher, when I mean pressure, the barometric pressure reading of the field, we would make it negative and subtract it from the IA. All right, let's do a pressure altitude example. We have a current altimeter setting of 30.1 inches of mercury and field elevation of 1,000 feet. Well, we know the pressure altitude equation is 1,000 for the field elevation, that's our indicated altitude, plus 29.92 minus 30.1 inches times 1,000. Well, if we take the difference between 29.92 and 30.10, we get 0.18. We're making it negative because the pressure, barometric pressure that we measured or recorded showed that it was higher than 29.92 inches. So the air pressure is heavier, denser. So we're going to multiply that minus 1.8 times 1,000, we get a negative 180 feet. Now we take the 1,000 feet plus the negative 180 feet, and we have a pressure altitude of 820 feet. Again, we subtracted the 180 feet because the pressure that we're getting on our barometric setting, when we listen to our AWOS or ATIS information, was heavier than the standard 29.92 inches. And over here on the right comes out of one of the FAA booklets. It's basically a correction factor that you can use to determine the pressure altitude correction table if you wanted to look up that data. All right, so what is density altitude? Well, this is the altitude that it feels like the aircraft is flying in terms of aircraft performance, in regards to the engine performance, the wing performance, the propeller performance. It is, again, density altitude is a pressure altitude corrected for non-standard temperature. It's the altitude in the standard atmosphere corresponding to a particular value of air density. And again, it's how the aircraft will perform at that particular air density. Again, density altitude is mainly affected by temperature, but humidity also plays a factor as well, but it's a smaller effect, and the equation that they use for determining density altitude doesn't reflect humidity, but it does play a factor. So the basic equation for density altitude is pressure altitude plus 120 times the actual temperature outside minus the international standard atmosphere temperature for the particular altitude that you're flying at, pressure altitude that you're flying at. So let's look at a density altitude example. If we have a pressure altitude of 4,000 feet and the temperature is 20 degrees Celsius, and we have an altimeter setting of 29.5 inches, let's just kind of go through the math. Well, the density altitude is, again, at 4,000 feet, that's our pressure altitude, first part of the equation, plus 120 times 20 minus 7. Well, where did we get the 20 right there in the given? It's 20 degrees Celsius out. Where's the 7 come from? Well, the 7 is associated with being up 4,000 feet in elevation from the standard data plane. If you remember right, at sea level, we're at 15 degrees Celsius. At 1,000 feet, we're 13 degrees Celsius. At 2,000 feet, we're 11 degrees Celsius, and so on. So if you go up to 4,000 feet, the standard temperature that it should be at 4,000 feet is 7. So that's where we come up with our 20 minus 7 times the 120. We do the math out, and we see that we have a density altitude of 5,560 feet. So on a hot day at Logan Airport, a high density altitude would make the aircraft feel like it's performing as if it was taking off from Mile High Airport, Denver, Colorado. Again, if Boston Logan Airport had a density altitude that day of 5,280 feet. So what are the effects on pressure altitude and density altitude? So again, pressure altitude is altitude displayed on an altimeter when it is set for 29.92 inches of mercury by twirling that knob there on the left-hand side. The aircraft performance is based on density altitude as it's flying along, relative to temperature. So again, pressure altitude is indicated altitude corrected for non-standard pressure. And then the density altitude is the pressure altitude corrected for non-standard air temperature. if you notice in this figure here, just get my pointer on, we could have 29.92 inches of set into the Colsman window and being flying at 5,000 feet pressure altitude, but our true altitude above the Earth will depend on what the temperature is. And so the density altitude is, again, the pressure altitude corrected for the temperature that we're flying through at that point. So at very high temperatures, 30 degrees Celsius, our pressure altitude is still 5,000 feet, but our true altitude is much, much higher. As we get cooler, let's say we fly into a cold air mass and the temperature goes down, we're still showing a pressure altitude of 5,000 if we have 29.92 inches of mercury or 29.92 inches dialed into the Colsman window on the altimeter. We would have a much lower true altitude. And as we get colder, our true altitude would get lower and lower. There's a saying in aviation world, when you're flying from hot to cold or high to low, watch out below. As you can see here, what you would notice is your altimeter will continue to show that particular altitude with 29.92 inches in as you go through colder and colder air masses, but your true altitude above the Earth is getting lower and lower. That's why we want to watch out below, whether it be the temperature going down or we're going from a high pressure to a low pressure. So why does pressure altitude and density altitude really matter? It allows pilots and aircraft manufacturers, but particularly pilots at this stage, to know how well the aircraft's going to perform. In many of the aircraft I fly, if you look at Section 5 of the Pilot Operating Handbook, you'll wind up coming up with all the performance characteristics of the aircraft. This is an example of climb performance versus best economy cruise performance. And you'll notice on the left side of both of these diagrams or charts, you will see pressure altitude on the left, and on the bottom, you will see temperature, outside air temperature. And so when you match the outside air temperature to the pressure altitude you're flying at, and then work your way over to the right, you'll be able to determine your rate of climb here in the left chart. And if you look on the right chart, you'll be able to determine your true airspeed depending on the power setting that you've got. So, again, pressure and density altitude are important to us because they determine our takeoff distance, our climb rate, our max ceiling height, our cruise speed, our fuel burn rate, our flight duration, and our landing distance, and a few other things. So how do we obtain pressure altitude? Well, again, the easiest way is to, if you're at your airplane, is to turn the altimeter knob so the Colsman window reads 29.92 inches of mercury, and then just read the elevation that's showing on the altimeter. It's not necessarily convenient, but it is a way to get your pressure altitude very quickly. Option 2 is to go through the calculations that I just went over. Option 3 is to use a tool such as e6bx.com's website. They basically, you bring it up, you click on pressure altitude, and you can type in your nearby airport, or you can enter the barometric pressure and field elevation, and it will give you the pressure altitude. And option 4 is to use an old school E6B whiz wheel if you've already been given the density altitude and the temperature. They've got a chart window on the E6B whiz wheel that allows you to put in the density altitude and the temp, and you can read off the pressure altitude, or vice versa. If you have the pressure altitude and the temp, you can get the density altitude. Well, how do we obtain the density altitude? Again, we can use the formula that I just went over. 2, again, you can use a free tool such as e6bx.com, click on the density altitude, and then take it from there, put the airport code in there, and you get the density altitude. And again, you can use the E6B whiz wheel if you want to go old school. And if you already have the pressure altitude and the temperature, you can determine the density altitude. So that's pressure altitude and density altitude, what it is, why we care, and how we go about determining them. Hopefully you found this video helpful. And if you did, make sure to hit the like button and subscribe to the channel so you get notified of my next video.